All right, now we're gonna do cheapest flights within K stops. So take a moment and read this problem on your own. This part is pre-recorded, so I'm going to just assume that you've seen it. So in this problem, there are going to be n cities. It is going to be a directed graph, and you're given a list of edges from a city to a city, and then the price for that edge, which is going to be the edge weight. And so you are also, in addition, given a place to start and a place where to end. K is basically how many stops between the source and the destination. So for example, if I was planning to start here at 0 and end here at 2, I could do this if K equals 1, because there'd be one stop in between. All right, so the crux of this problem is basically I want to return the cheapest path for getting from the source to the destination. It's possible that no such route exists. Maybe the path is too long and basically K is too small for you to reach the destination. All right, so I'm going to show you a few ways to get this problem wrong. It's actually, when approaching this problem with Dijkstra, it's actually pretty easy to mess up in a few different places. So I'm going to show you this solution, and I'm going to go over it a little bit. So here is the graph that I'm building. Basically, I'm going to build a directed graph where, for example, 0 in my hash table might have a list of destinations it can go to. Maybe that is 1, right? That is the destination, first element of the tuple. The cost is maybe $700, for example. And then maybe it's also able to go to some place like 4, and that is going to cost $300, for example. So that's basically the graph data structure. It's an adjacency list. Moving on, I have a table of costs. This should look very familiar to the template for Dijkstra's that I've given. And I initialize the cost at 0, and here's that tuple. Here's where I start. The cost is 0. Remember, with the priority queue, I'm going to be using cost to figure out which thing in the queue I should look at first. And remember, Dijkstra is a greedy algorithm. We definitely want to look at things that cost the least and consider them first, okay? And here is steps. So I start at -1, which might be a little bit unintuitive, but basically through K different stops, you'll arrive at the destination. You could also start at 0 and then quit when steps equals K plus 1. That's also valid. So when I start the while loop, I basically pop off that first element, and then I see if the current node is the destination, and then I return the current cost. If the steps is equal to K, then I know that there's no more steps for me to advance from here, so I just don't consider looking at that node's neighbors. Here's where I actually look at the neighbors, and notice here I'm doing the same thing that I've done in previous examples. I look at the next cost, and I take the current cost that exists at the current node, and I'm seeing how much it's going to cost to get to the other nodes by adding their additional cost. Remember, this is what it looks like in that tuple when I have the first element as the neighbor and the cost, the edge weight for that edge to get there. So if I have already considered a cost to that neighbor that's less than or equal to this cost, I no longer consider it. But if I have, then I'm able to basically update my cost table and add that neighbor with the advanced steps and the advanced cost onto the queue. If I can't find anything, then I return -1. All right, so the key question, why doesn't this code work? So take a moment, pause the video, and try and figure out why the solution won't work. Well, hopefully you thought about that. And one of the reasons why it won't work is basically it's possible to have a test case where basically the shortest path is actually equal to 7, right? 7 is going to be the answer. So it first considers 0 onto the queue, right? And then it notices this 1 and this 3, right? Because those are the immediate neighbors, right? So these two things get added onto the queue, right? So now 1 and 3 are added onto the queue. But what's going to get popped off next? Well, it's actually going to be this 3. And why is it this 3? Because it has a cost of 2, right? This 2 is smaller than this 5, and that heap that heap prioritizes things that are lower in cost, right? So if you look back at the code, the heap is going to compare the costs first. And the smaller cost wins, so it gets popped off, right? So now 3 is the next candidate. So far we've visited 0, right? And now we're considering 3. And then 3 looks at its neighbors, it's only got 1. So it enqueues this 1, right? But at a different cost, not at 5, but at a cost of 4, right? So 4 is now the min cost to get to 1, right? And this is what the heap looks like currently after enqueuing this 1, okay? So we have a cost of 4 and a cost of 5, right? Of course, it's a min heap, so we're going to use this, right? When this cost of 4 at node 1 gets used, it's going to look at its neighbors, right? So who are its neighbors? Well, it is going to look at this 4, right, and this 2, okay? So now the heap, is going to look like that 5, 0, 1, that's already in there. But additionally, there's going to be this 6, 2, right, 2 because we add one more step. And this is that destination node 4. And we're also going to have a destination node 2 with also this 2. And what's this going to be? This is going to be, well, it was 4 here, and you add this 5, so this is 9. Okay, good. So this is what your heap looks like now. It has 3 different elements, here, here, and here. And when we look at a node next, what's going to happen? Well, 5 is the least cost now, right? 5 is the least cost. But based off of our code, we notice actually that it is going to try and visit the neighbors, right? 4 and 2, but we just saw them at a smaller cost, right? So when we pop off this 5 cost to get to node 1, we actually won't be able to enqueue this 4 and this 2. We will not be able to put them on the priority queue. So in effect, this is kind of a no-op. 5 won't be able to do anything. So the next time is we're going to look at this 6 right here. But once we pop that off, we are prevented from going any further because the steps is equal to k, right? So notice for this problem, k equals 2, right here. So we won't be able to go any further. So this 6 also becomes kind of a no-op. And then finally, we dequeue the 9 cost to get to 2. And basically, we return a cost of 9, right? Which is decidedly not the answer, right? The answer is going from 0 to 1 to 4 and then to 2, right? So that is this path going here, and then we go here, and then we go here, right, in the white lines. So we're not able to do that, and the key reason why this algorithm fails is because it's kind of like this. By ultra optimizing to get to the lowest cost to reach to a node first, and then screening out other ways to get to that node at a higher cost, we're actually preventing us from finding the correct answer. Another way to get an intuition about this is that this algorithm that we have that doesn't work ultra optimizes to find the shortest cost path to some intermediate node, And that prevents us from reaching that node at a higher cost, but less steps, right? In this problem, we have to optimize on 2 different dimensions. And by optimizing on only one, we basically stop us from reaching the correct answer at a lower cost, right? The crucial thing was we needed to take this edge, this 5 cost edge, even though it costed more, so that we had access to more routes in the future, right? We then needed to take this 4 as an intermediary, right? But when we took this 3 and this 1, we weren't able to use this 4 as an intermediary anymore, okay? That's the key reason why this solution fails. So here's just a summary if you follow along on the slides. Basically, when you take the least cost path all the time until you're maybe close to the end, you become desperate, right? Because you're starting to run out of the other resource, which is the amount of steps you can take. And then you'll get desperate because you're going to take an edge no matter how high of a cost, as long as you can just reach the destination. So it's possible, actually, that if there's a cheaper path that takes a longer amount of steps, you're not going to be able to do that with the algorithm that's just above. Okay, another way of saying this is that you can arrive at some intermediate node with more cost, and you should allow this to possibly happen, because if you can do that in less steps, that is a possible place to start from to get to the answer, okay? It opens up a path to arrive at the destination, perhaps at a lesser cost. This is the example. I don't have my picture from Freda exported yet into the slides. But here is a fix for it. Basically, there's going to be a few differences, I'll note. We can prioritize on the number of steps. Basically, the ones that have gone less steps in the queue get prioritized first. And this solution is actually very similar to SPFA, okay? Notice that another difference is that I don't have a condition to return once I have found the destination node, okay? This is very similar to SPFA, where we keep considering possibilities until the queue is actually exhausted, right? And then that difference is also reflected because I have to return the minimum cost at the end from the cost table. All right, so this for loop is very similar, but there's a key thing also to keep in mind because of the way we've done prioritization now. Remember, what we've done is we've switched the positions between the amount of steps we've taken so far in that current node of the queue and the cost to arrive at that node. So if we get down to this statement here where we prune, this means actually a little bit something different, even though this piece of the code is exactly the same. Because our priority queue shows us the least cost way, in terms of steps, it costs the least amount of steps to arrive at a node. If we've already done that, we've already considered a possibility that is both less in steps and less in cost, okay? Less in steps and less in costs. So that's why this pruning ends up meaning something a little bit different because of the way we've switched the positions in the priority queue, okay? It's a pretty subtle thing. And hopefully you'll be able to compare this to SPFA, which is on that presentation that we did with decks and queues. Okay, but I'm not done yet with this problem because I want to show you another way in which you could perhaps easily screw up, which is something that I've done. So I'm going to go over this, and also once I'm done, I'll tell you to pause the video and you should try and figure out why it's wrong also. So same deal here. I set up the graph and I arm the queue with our starting node, and I use the cost to prioritize first, and then the steps second, and then the destination node you can think of as just metadata, right? I have my guard clauses here, which is the same as in the first solution. And here, I have something a little bit different, okay? The amount of steps that I've taken to arrive at a current node is now what I'm going to use as my table that I'm going to use for pruning. So the amount of, if I've seen this neighbor in a lesser or equal amount of steps, then I'm going to not consider this neighbor anymore, okay? I am simply going to ignore it. But if this is a lesser, if this costed less steps to get to this neighbor, I'm going to consider it, okay? And then I'm going to update the steps right here. Okay, so pause right now and try and figure out what's going to go wrong in this example. Okay, now that you're back, this is why it's incorrect. The correct output might take more steps, right? But it might actually cost less. Okay, it's possible that in a graph, and we actually can use this same test case to take a look at that. Okay, we know that the least cost path is going to be in terms of cost, right? Is going to be from 0 to 1 to 4 and then to 2. In terms of steps, there's a quicker way, right? You could go from the 0, right? And then you could go to 1, and then you could go to 2, okay? And the cost for that is actually 10, right? Which is decidedly not the least cost path. So again, this solution tries and optimizes on only one dimension, right? And that leads to the incorrectness that we're seeing, is when you try and optimize on the number of steps, even though the heap is doing some prioritization about cost, you won't be able to arrive at the correct solution. So we can take a look at this example. Remember, the priority queue, right, prioritizes on cost, right? But we also have our min cost table, which is pruning based off of steps, okay? Okay, where's this going to lead us? Let's just step through this. So we start at 0, and we enqueue two things. So the least cost steps to get to 1 is going to be, let's say, this one step. Technically, we start at -1, so a little bit unintuitively, this is going to show up in our table as 0, and this is also going to take 0 steps recorded for node 3, okay? But then we pop off node 3, right? So node 3 is the one we look at next, and it has a min cost of 2, okay? And 3 is going to try and enqueue this one, okay? But it is not going to be able to do so because of the pruning. So the pruning that we do, remember, that is right here, we've seen this neighbor, right? The neighbor is 1, but we've seen it at 0 steps so far, and we're basically now considering whether 1, right, is possible as our min steps to get there, and it isn't, right? Because 0 is less than 1. Okay, so where does that leave us? Now we have to explore this 1, right? And it took us 0 steps to get there, so the total cost so far is 5, right? So we have 5 cost, and now we are considering enqueuing 4 and enqueuing 2, okay? We successfully put both of them onto the queue, right? Because they have never been looked at before. So 4 gets enqueued, right? Total steps is 1, and 2 total steps as 1, okay? So what happens now? We look at this 4, right? We dequeue it now, okay? And when we dequeue, we look at its neighbors, and we see that, hey, we could get here with a 2 steps, right? 2 steps to get to 2, but we get pruned, right? we're not actually allowed to enqueue that because this stops us in our tracks, this if guard, okay? So now we're left with just dequeuing 2, and that's going to leave us with a total cost of 10 because the edges that we looked at were this 5 and this 5, okay? So in this algorithm would return 10 to get to this 2 as our destination, and we know that the correct answer is actually 7. Okay, so this fails for this test case. This also suggests about what the right answer might be. Perhaps we need to factor in both the steps and the cost into the solution. The previous correct solution did this by also giving us an invariant, right? The moment that we saw this cost for this neighbor, if we've seen it in less steps and less cost, then we shouldn't consider that neighbor, right? There's another way to write that into our code, and I'm going to show you the following way. The following way would maybe you can either zip this up as an array of tuples, or you can simply use 2 different arrays, right? I both keep the min cost and the min steps, and if only one of those things, right? If one of those things is better than the best seen, then we allow ourselves to consider that possibility further, okay? So more concretely, maybe the next cost might be greater or equal to than the cost of a neighbor that we've considered before, but its steps might actually be less, right? So if one of these expressions, right, this is the first expression for steps, is the second expression for costs, if one of them is false, then maybe we should consider it, okay? And then we can record that into the answer here, okay? And then we can update our costs and our steps table, okay? This allows us to do that early return because once we see that current node as our destination, we know that that must be the least cost way to arrive at that node. One thing I'll point out is that at the end of a solution, of this solution, your cost table might not actually be correct, right? It's possible that you might have had a solution that took less steps, but maybe a higher cost. And that's possible that depending on the order of the nodes, this cost table might be mutated in such a way where visiting a current neighbor, perhaps even the destination, might actually be higher than what the true answer is, right? In this case, we can't rely on the cost table to give us basically the single shortest path to all nodes. But when we pop it out, we'll still be able to return the minimum cost to that destination node because of how the heap orders its elements. Okay, personally, I find this solution a bit more intuitive than other ones. The key expressions are right here, is in this if statement, right? This allows an option where if a node can be explored with less steps but more cost, we allow that exploration. Also, if we see something that takes less cost but more steps, we also allow an exploration from that state in the graph. Okay? The heap also synergizes with this solution because when we eventually find that destination, we know it is the minimum cost to arrive at that node. All right, so let me conclude on these mistakes that I've made now, and hopefully you won't have to make them. Solutions generally have to allow for reaching a node with higher cost because reaching that node might happen in less steps, right? Which allows you to optimize the solution later, okay? So BFS, like traversals work, such as SPFA, because we expand from the steps and not the costs. We might actually explore a node in the base graph multiple times at different costs and at different steps. So we've seen two approaches. We saw SPFA in a previous presentation, and now we've seen two approaches using Dijkstra. Okay? In Dijkstra, one thing we could have done was prioritizing steps. This looks a lot like SPFA. And another one is to prioritize cost, but you allow paths with less steps to be dequeued as well and explored. So this other question, the last one that I had, is find safest path in a grid. I didn't go over this live, but I'm re-recording now, so hopefully you get to enjoy this problem. I think it's a good one. There's multiple very interesting approaches to it. In this problem, you're given a zero-indexed 2D matrix grid of size n by n, so the length is equal to the height, and each cell represents, well, a cell containing a thief or an empty cell. You're also initially positioned at the top left corner, so you're going to be starting from here, and you're going to try and find a way to get to the last cell. So the safeness factor path of a grid is defined as the minimum Manhattan distance from any cell to any thief in the grid. So for this cell, the minimum distance to thief is 0, right? Because you start off right with a thief. Okay. What about this cell? Well, the distance would be 2, right? Because you can go right left, because you can go right down. You can also reach a thief by going this way. Okay. So each cell is basically going to have some measurement of safety. So each cell, there exists some measure of safety. And then, if you have the measurement of safety for each cell, you could probably plot a way that is the safest in order to reach the destination. So pause the video and figure out how you might do that. And I'm going to start talking about that in 3, 2, 1. Okay, so hopefully you see the relationship between this problem and other problems before. If you watched the Dex and Q's video or the breadth first search one, hopefully this one is going to be more familiar because you can actually build that safeness grid using basically breadth first search, and that's basically what I do. I basically find all of the ones, right? And from all the ones, I can start expanding, right? I know now that this safeness factor is 1, this safeness factor is 2, right? Because you start out here and you just start expanding, right? In this way, you can compute the safeness grid, which is what I have. So that's this. This is very similar to that problem as rotting oranges, but it's almost like a sub-problem for this problem. This problem gets rather involved because now with the safeness grid, you can use Dijkstra's algorithm, okay? And this is pretty classic for Dijkstra, okay? Where, first of all, where do we start? Well, we want to start off in the top left corner, right? That is these two things right here. And we also want to prioritize on cost first, which is why that's the first element of the tuple. With the safeness grid, I can just use that value. Remember, we want to prioritize getting the safest route, okay? So the higher the number for the safeness grid, which is the distance to a thief, right? If we have 4 distance to a thief, we might want to prioritize a cell that's safer than maybe a 3 or perhaps 2 distance to a thief. If we were just to have these values 4, 3, and 2 raw in the heap, we would get the value 2 first, then the 3, then the 4, right? To invert that relationship, that's why we use a negative sign, okay? That's because it makes big values like 4, right, on a number line, all the way to being the smallest value, right? -4, -3, -2. So now with these values arranged, we can now go through Dijkstra. So I keep basically a visited grid, right? And I'm going to keep how safe it was to get to that particular node. Okay, because it's possible when you can visit nodes in various directions that the safest path through the grid might actually end up looking like that, right? Okay, so this is pretty now classic Dijkstra. Hopefully this is pretty boring to you. Once we reach the end node, we just return that minimum cost, but of course we need to flip the value now, right? Because safety values aren't going to be negative, they're going to be positive. So we flip the negative value to be positive. We do some arithmetic here in order to find the neighbors. They are in 4 dimensions, right? So when we enqueue, we can now say that if it hasn't been visited before, we can say now that it's visited, and we won't ever have to look at it anymore because that property of Dijkstra's, remember, is greedy. It was the least cost way to visit this row and column, and we can enqueue the least cost ways to get to that next row and that next column. And finally, we just enqueue on more nodes, and this just cycles through until we reach the final node. A key thing to note is that safety value is going to basically be the maximum safeness factor in that entire grid. Okay, while recording this bit, I noticed something pretty unusual about the shape of Dijkstra in this problem. It's that we don't actually have a min cost table. It is literally conflating visited with enqueued. Remember how I said earlier in this presentation that when doing Dijkstra in general, these two things are not the same thing, okay? And I thought about the reason why you're able to do this. I think it has to deal with the fact when you look at the grid, basically the difference, the change, can only be changed by 1, right? Also, unlike in a general graph for a grid, you can only reach this node through its adjacent neighbors, right? So the difference in safety, the delta can only be as big as 1 at most. And because of this property that you're able to do that, this kind of suggests that maybe Dijkstra isn't actually the most efficient approach that you could make. There's probably a faster algorithm where you can maybe choose the safer option without using a priority queue. Okay, so that's all I have for that problem, but if you wanted to change this into a min cost table, this solution should functionally work just as well. But just keep in mind that if you see this, it's actually very likely that an optimization to your Dijkstra algorithm is possible. When you do mark visited, it's going to be after you visit something, right? So visited, next R, and next column, okay? All right, so that's all I have for that particular problem. One note about this is that this problem is solvable using binary search. While I'm recording this, we never got to a binary search part 2 presentation, so that isn't within this series so far. But I encourage you to look at the binary search solution, or maybe try and come up with how you might do that on your own, but we won't be going over it. Okay, I'm now going to go over design a graph with shortest path calculator, but because this is small group work, I encourage you to actually try the problem before watching further. So for this problem, you're going to be building a graph. Okay, you're first given a number of edges and you can initialize your graph, but you're also going to have some number of calls for add edge, and you're going to have some number of calls for shortest path, and the calls between add edge and shortest path are going to be intertwined, right? So you might get a call to add edge, then a call to shortest path, and maybe a bunch of add edges, and then maybe a bunch of shortest paths. So your goal is to basically return the correct answer for every time the shortest path is called. In order to do that, your add edge should update the graph and do whatever you need to do. Shortest path, hopefully if you're looking at this presentation, you'll realize that, hey, Dijkstra actually really fits this pattern really well. I'm actually just going to speed things through and bring up the code now. So here's the graph. Apparently I did this in Java a while ago, so that's why you see this here. And I'm building an adjacency list. All right. So when I add edge, I simply just modify my graph. That's all I do. This is a 2D matrix, actually, from what it looks like. And when I calculate shortest path, well, I'm using a priority queue, so this is classic Dijkstra. And I break the loop once I have the current node of where I am right now, and that is equal to that destination node, node 2. And then I just simply return that cost. In this priority queue, I'm actually using a comparator, which I'm much more comfortable with. I am storing the cost as the second element of an array, and the first element is actually the node position. I think this is actually the node itself, so this might be 1 or 2. Here is where I loop through the neighbors, and you can see me care about that min cost table here. And only if the new cost is less than the least cost that I've seen am I going to update my cost table and be able to enqueue that. So notice again how I don't conflate visiting something with enqueuing something. It's possible to reach a neighbor at a lower cost, and I allow that to be possible using that cost table, right? And then I update it selectively. When I eventually dequeue that neighbor, perhaps it's already in the queue, right? But at a higher cost than the minimum, then every neighbor that it's going to look at is going to have a higher cost than the previous time that it looked at that neighbor. Right? So your queue, let's say your priority queue, might have visited 1, but with a cost of 50, but this 1 is also in the queue with a cost of 55. Well, when this node 1 looks at its neighbors, right, it's going to have 50 plus whatever cost X, 50 plus cost Y, and 50 plus cost Z, right? Those are all going to be smaller than 55 plus X, 55 plus Y, and 55 plus Z. So none of these things will get enqueued, okay? So that's that. This problem hopefully is very, very straightforward to you, but if it didn't make sense, try some of the problems from earlier on in the presentation on your own, and eventually it will sink in through just enough repetition. Okay. One final note is that Floyd-Warshall can be used for this problem. This allows you to trade the other way in terms of time complexity, right? Because you can pre-compute the shortest path from all nodes to all other nodes, and so then you can return shortest path in O of 1. But the first time that you need to change the graph, right, through an add edge operation, you might actually need to recompute the shortest path throughout everything, okay? You could also maybe wait and see until shortest path is called and then do the computation there. Because if you have a sequence of, let's say, add edge, and maybe you have a sequence of this like maybe 10 times, maybe you don't need to compute shortest path until you're asked for then shortest path, right? So keep that in mind. This is an n-cubed, but this also works as a strategy. Just depends on your design goals. This path with maximum probability, I think you're more than ready to start tackling this problem. Hopefully it is a rather transparent application of Dijkstra's to you. But if not, take a moment and maybe just review different parts of this video. I think safest path in a grid is maybe something you might want to check out. We're looking at that inversion strategy. when you want to prioritize looking at nodes with the maximum probability, even though you're using a min heap. Okay, so there's slides, of course, and there's also homework, and you can find the slides online. And there's also challenge problems as well. But as a final note, thank you so much for taking the time to learn and practice Dijkstra with me. So you can send at me at this email address. Have a nice day. See ya.